In this video, we talk about decomposition of combined loads. This is the first of two parts of asking how we deal with forces that result in more than one type of load. So we see examples here where a force is at an angle here so that it's neither an axial load or a lateral load. It has some of both. Here, a force is in the axial direction, but it's off-center, so it would create a moment, which is a lateral load that bends it, but it also would compress it. And this here, again, bends it, but it's also off-center, out of plane, that would cause it to twist. So these are some examples of forces producing more than one type of load. So when we consider combined loads with beams and bars, we've learned to calculate these individual types of internal loads: axial, torsional, shear force, and bending moments. And from those, we've answered questions about failure and deflection. However, all of those are limited to these very simple types of loads. And so most real-life situations we could not address with those skills. So what we do now in this thing is to recognize loads that do not result in pure axial torsional loads, and we decompose them into the loads that we know how to address. So if a force is at an angle, this is the simple thing that we can decompose an angled force. This here, everything's in the XY plane. That angle does not mean anything about the Z direction here. We're just decomposing it into F sine theta. Now in this case, theta is the distance from that Y axis, and so sine then is the opposite from the angle here, and so that's why that's F sine theta. And that's a lateral load, and then F cosine theta, that's an axial load. So this decomposition is exactly the skill we have used to write equilibrium equations for forces at angles. The next question we have is what happens if we have off-center parallel forces? That is, it's a force parallel to the beam, and we refer here to this are in plane because it's off center by a vector that's in the same plane as the force and the bar. Everything's in plane. So this decomposes into the axial load and into a bending moment. A common cause of this type of forces are ones that act on the outer surface of the beam. You don't actually need a crossbar to get this off-center parallel force. And so this may look familiar if we had, pointing out, equal forces on both sides of the beam. That would just translate to a force of 2F in the middle of the beam, because the moments created by that are in the positive and negative direction and would cancel. If instead we had forces that are on the opposite side of the beam and in opposite directions, then the forces cancel, and instead what we're left with is that moment. So we learned previously that that causes a pure bending moment, which we also called a couple. So what we see here is that in the past, we were always, anytime we had an off-center parallel force, we were balancing it to cancel either the force or the moment in order to deal with it as a pure axial load or a pure lateral load. But now we realize we may need to decompose it and deal with both parts of the problem. An off-center perpendicular force is out of plane. So this is one where the force F is perpendicular to both the long axis of the bar and to the vector here, B, which is coming straight towards us in the Z direction, between the central axis of the bar and where force is applied. So again, this can decompose. There's clearly a lateral load here because we're pulling on the beam sideways. But then there's also this torsional, which is the B times F. And so that's what we see here. And again, like before, this could simply be created by pulling on the front of the bar. So I could put that here. But if we had pulled on both the front and back of the bar, this would turn into a pure lateral load here of 2F. And if we had pulled on the front of the bar and the back of the bar, both times here with F, we now have that distance R over 2 in between them, but then we multiply by 2, so we have both, and so that is then RF, and then that is a pure torsion. So this is, again, we've seen these same types of forces that we're drawing here. We've seen this type of thing. It's just that in the past we always balanced it. Now we have to be ready to decompose it so that we can deal with both types of forces, both the force and the moment creating this. We can also have off-center forces at angles. So this here, everything is in plane here. So what we have is we have the vector from the central axis out to where force is applied that's perpendicular to the long axis of the beam, and then we have this angle at this position theta. This time we've chose to draw theta from the x-axis. Again, these things can be defined different ways, just be clear what they are. So we'll go ahead and draw this out. We could decompose this up here into a force of magnitude. This is going to be sine theta, and this will be cosine theta, the adjacent. So the upward is F sine theta, plus also at the same point a line here that's F cosine theta. But we'll notice these are also, at least this first one is also a, in this case, off-center axial load. So we can switch that to a on-center axial load, sine theta, and then there's a moment created by this distance here, which is the radius r. That moment is bending it this way, and this is a bending moment around the center point of magnitude rf sine theta. And then this here, this other one, is a lateral load. So in the end, it is the sum of these three sets of loads that give us a pure axial load here, and then both of these ones are types of lateral loads. One of them is a lateral force and the other is a bending moment, but both of these are going to cause movement, bending in the xy plane, that is in the y direction or the x direction, where this beam is in the y direction. So lastly, we may have off-center forces at angles out of plane. So in this case, we see that the forces here are all in the xy plane. We're looking at it, but the vector between the center of the bar and the force is in the z direction, directly away from us. So when we decompose that, this will be decomposed into a axial load off center, but this time over here in this z direction, and then this load here again off center, but a lateral load, and both of those decompose this time. So this is an axial load of magnitude f sine theta, and then this is hard to draw, but there is here a moment here. And this is a moment, it's a bending moment, so we'll write it as m, but the bending moment is around the x-axis. So it's a bending in the yz plane, but that has a magnitude rf sine theta. So we have both of those, and then from this f cosine theta, we have that can look like, on the central axis, an F cosine theta. So now we've bent it in the z direction, but now we're also bending it in the y direction. And so those are lateral loads in two different planes. And then finally we have the this is simply a torsional moment here, and we can write it as the downward arrow in order to put our hands in that position, our right hand in that position, and it's RF cosine theta, and that's a torsion. So we see this one results in an axial load, bending loads in two different directions, and a torsional load. So we can also get combined loads simply by decomposing independent loads. So we might have multiple independent loads. So maybe there's a bending moment here. Maybe at this point there's a torsion T1. Maybe that was M1. There could also be a P1 here. There can be arbitrary types, and maybe we're also pulling here at an external force that I'll put as N1. So we could have all sorts of different types of loads on this. Similarly, we could, in theory, even be pushing on it in different directions. So maybe there's a P2 here, or there could have been an angle. There's an arbitrary number of things we could do to this beam. Now, because these are separate, it's pretty trivial to figure out how to decompose these. We just have to think of bending moments in each coordinate axis, or bending lateral loads in each direction, and axial and torsional loads. So after decomposing these loads, the next part of the process to solve problems with combined loads is to solve the problems separately. So we can draw separate figures as axial, torsional, and lateral loads, and then we can use each of these to solve using free body diagrams for the internal loads. And we can finally, once we've done that and solved the problems, we can calculate stress and deformations due to each type, and we can superimpose them. And this is covered in the next video. Thank you.